Heterogeneous equilibria. Hello everyone, I'm Dr. Vicky. In this session, we will learn about heterogeneous equilibria. Unlike homogeneous equilibrium, heterogeneous equilibrium applies to reaction in which reactants and products are in a different phases. For example, when calcium carbonate is heated in a closed vessel, the following equilibrium is attained. The two solids and one gas constitutes three separate spaces. At equilibrium, we might write the equilibrium constant as the concentration of the product divided by the concentration of the reactant, which again we use K prime here to differentiate it from the final form of the equilibrium constant. Likewise, pure liquids, solids are also not included in the expression for the equilibrium constant. Hence, we can write back the equilibrium constant Kc, which is equals to concentration of carbon dioxide. Or we can write back Kc is equals to K prime times by calcium carbonate concentration divided by calcium oxide concentration. Alternatively, we also can write the equilibrium constant Kp is equals to partial pressure of carbon dioxide. The figure shows that the reaction was carried out at the same temperature with a different amount of calcium carbonate and calcium oxide. From the experiment, we can conclude that the equilibrium pressure of carbon dioxide is the same at the same temperature despite the presence of different amount of calcium carbonate and calcium oxide. So we can conclude that the partial pressure of carbon dioxide does not depend on the amount of calcium carbonate or calcium oxide. Now, let's try some example. Example 1. Consider the following heterogeneous equilibrium. Calcium carbonate in a solid form decompose or dissociate become calcium oxide and carbon dioxide in the gas form. This equation is heterogeneous because calcium carbonate in the form of solid, calcium oxide in the form of solid, and the carbon dioxide in the form of gas. At 800 Celsius, the pressure of carbon dioxide is 0.236 atmosphere. Calculate A, Kp, that means equilibrium constant in terms of pressure, B, Kc, equilibrium constant in terms of concentration for the reaction at this temperature. Now let's look at the solution for example 1. Using equation in example 1, we can write equilibrium constant in terms of pressure is equals to partial pressure of carbon dioxide, which is given in the question 0.236. Remember, even though it's the partial pressure, we don't use unit in a equilibrium constant. For B, where we need to find Kc, this equation have to be used where Kp is equals to Kc times by 0.0821 times by the temperature, and the difference is the number of mole. In this case, the temperature is given is 800 Celsius. So before we substitute in the equation, we have to convert the 800 Celsius into Kelvin, where 273 need to plus and get 1073 Kelvin. The difference in the number of mole is the total number of mole of product, which is 2, minus the total number of mole of reactor, which is 2 minus 1 is equals to 1. So we substitute this value in the equation and obtain the Kc, where Kc is equals to 2.68 times 10 power of negative 3. Now let's look at the example 2. Consider the following equilibrium at 295 Kelvin. The type of equilibrium is the heterogeneous equilibrium because it involves two types of the phase, which is solid and gas. The partial pressure of each gas is 0.265 atmosphere. Calculate the Kp and Kc for the reaction. Now let's look at the solution for this question. As we know, ammonium, hydrogen, sulfate in the solid form. So we omit the concentration of ammonium hydrogen sulfate from the equation. Hence, the Kp become the partial pressure of ammonia times by the partial pressure of hydrogen sulfate. So we will obtain the answer 0.0702. For Kc, we will use the equation Kp equal to Kc times RT power of the difference in the number of the mole. In this equation, the difference in the number of mole is equals to 2, the total number of mole of the product minus the number of mole of the reactant, which is 1. So 2 minus 1 is 1. And the temperature is given in the Kelvin, 295 Kelvin. By replacing or substitute the value in the equation, we will get 2.898 times 10 negative 3 is Kc for the reaction. So remember, we omit any pure solids or pure liquids in the equilibrium constant expression because their activities are uniting. So I hope this video helped you to understand chemical equilibrium in more detail. See you in the next topic. Thank you. Bye-bye.